My name is Syed, and I'm a research fellow at Smart Internet Lab at University of Bristol. So we have two topics for this slot. The first one is software-defined networking, also known as the SDN concept, and the other one is NFV that will be presented by my colleague Navdeep later on. So as you have noticed in the previous presentation, that how we are using the concept of NFV and SDN. So this presentation is more focused on the basic tutorial for the software-defined networking. So let's start. First of all, I will start with the limitation of the legacy networks. Then I will proceed with the SDN concept, and also I will define the SDN architecture and the key interfaces for software-defined networking. And in the end, I will just conclude my presentation with the advantages that software-defined network brings. So let's start with the limitation of the the limitation of legacy networks. So first of all, the legacy and traditional IP networks have integrated control plane and data plane within each forwarding device, such as routers and switches. Moreover, due to the tight integration of the control plane and the data plane, it brings complexity and rigidity in the architecture, where the innovation is difficult and also complex. And also it supports only single service at a time using the same infrastructure. So as you can see in this figure, where each router or a switch have a integrated control plane and data plane attached to it. So in terms of the data plane is responsible for forwarding the traffic, where the decision on where to forward the traffic among the devices is made by the control plane, as you can see in this illustration. So in terms of the control plane actually dictates how the traffic is forwarded among devices. Actually, it is distributed and decentralized across the network devices, where each router may be running a routing protocol such as RIP, OSPF, BGP, and so on, to exchange the traffic routing information with other routers in a distributed way. The traffic forwarding in these legacy network is based on destination IP address, destination MAC address, MPLS labels, and VLAN headers. And due to the decentralized and distributed nature, that brings a bit of difficulty in terms of managing all the switching and routing in a legacy network. Okay, in terms of device configuration, due to the tight integration of the control plane and user plane, the devices are very hard to configure, since a network administrator need to log into each device for the configuration itself. Typically, each vendor has proprietary software and hardware to manage the devices, where these softwares are quite expensive for each device to manage. To this end, actually, software-defined networks is a novel network architecture that actually solves the problem of traditional or legacy IP networks. In SDN, it separates the control plane from the data plane and adds programmability on the control plane. As for the data plane, the routers and switches just forward the traffic, and on the other hand, the control plane actually that is programmable, and all the control functions are shifted towards the centralized SDN controller that dictates the routers about the behavior that it should follow. As you can see in this diagram, where the data plane actually belongs to the switching and routing devices, and the control plane actually move towards the SDN controller. In terms of the architecture, SDN actually has 3 different layers. For the first layer, it is called the infrastructure layer, where all the network forwarding equipment are residing, such as switches or routers in the data plane, and they are responsible for processing packets-based rules provided by the control layer. The second layer is the control layer that actually provides the bridge between the application and the infrastructure layer via southbound and northbound interfaces that I will discuss in my next slide in more detail. And actually, this provides programmable platform to dictate the traffic for forwarding devices. The last layer is the application layer that contains the applications designed to fulfill the user demands. For example, cloud applications, management applications, or business application. In terms of interfaces, there are two key interfaces within the SDN architecture. The first one is the northbound interface that connects the network application with the software-defined network controller, and it has an API available to application developers such as CLI, REST, and so on. The other interface is called the southbound interface that connects the controller with the forwarding devices such as routers or switches. That is based on the well-defined protocol to configure the devices such as OpenFlow. It specifies functions or controller to access functions provided by the switching devices. And those functions actually include the reporting network status or importing packet forwarding rules for the controller. In terms of advantages, software-defined networking offers many advantages, such as, as compared to legacy network, it can provide a centralized way that enables consistent policy throughout the network. Moreover, the SDN controller, being a software, it can run on the community servers, as well as the network applications foster innovation, enabling custom policies and protocols. And considering there are like well-known software-defined controllers such as ONOS, Open Daylight, and Ryu are open source, thus pushing forward towards open source networking. Another advantage of the software-defined controller can be used as a provision network resources dynamically, in contrast to the manual pre-device configuration, thereby reducing the capital and the operating expenditures, significantly. For example, the SDN controller may offer services such as L2 VLAN based service from host A to host B, or it can deploy a router 2 to router 3, and the SDN controller will automate the network configuration. This allows an ecosystem where developers can build network applications to test custom policies and protocols without worrying about the network device configuration itself. So that's all from my side. If you have any questions, otherwise my colleague Navdeep can proceed with the other presentation.
Thank you, Syed. Some questions now. This is a concept that is more well known, so maybe you don't have so much questions, but I will nonetheless put you in a question. How important are these concepts to someone who is developing this software? How can they take advantage of this?
Yeah, of course. I mean, the concept of SDN and NFV is now well defined, and people are utilizing this for different applications. For example, in 5G as well as for transport networks. So, if they want to develop something based on these concepts, of course, they need to have a basic understanding how the architecture behaves and what are the interfaces that are supported within the architecture. For example, for the southbound interface, where they need to configure the devices from the SDN controller. So there are like basic concepts like OpenFlow and so on that are available, in the market that are open source. So they need to understand, of course, the complete architecture before they go on with the deployment for their own use cases.
So Steve Carroll has also a question: how does SDN support network slicing, and where does the NPV become relevant?
Sorry, can I see the question itself?
It's on your Q&A box.
Okay. Okay, yeah. So in terms of network slicing, of course, SDN, the concept of SDN is being used in 5G as a transport network. So if we need to support network slicing, we need, of course, there's research going on how the transport layer will be sliced to support the end-to-end latency for the future wireless communication system. I'm not sure about this NVP, so I cannot answer this one.